Okay, so here we have the code, source code, through which we can create a node. The first requirement is to create a node, and then only we can add up with the values in the node. So first you need to define a node having some data. References is to its left and right child nodes. So here we have a structure into which we have certain values like data, then we have pointer values, left child and for right child. This is self-referential structure. Now we'll see inserting an element in binary search tree. A binary search tree is constructed by repeated insertion of new nodes to the tree structure. Repeated insertion of new nodes to the tree structure means we are repeating the insertion process. Inserting a new node in a tree is achieved by performing two separate operations. Number one, the tree must be searched to determine where the node is to be inserted. And secondly, insert the node into the tree. This means that first you need to identify the location where you will be inserting the new node. Now the insertion will take place based on the value of the new node, because we have to maintain the property of binary search tree. The root node, the value of root node will always be greater than its left child node, and the value of right child will always be greater than the root node. This property should not be violated. So we have to take care while inserting a new node in the tree. Therefore, we need to first determine where the node is to be inserted and then actually insert the node in the tree. Now suppose data is data. Suppose we are taking a variable data is the information to be inserted in a binary search tree. Now we'll look at the steps. This data is the actual value that you want to insert in the binary search tree. First, you need to compare data with the root node. If data is less than the root node information, then proceed to the left child of the root node. If data is greater than the root information, that is, root information means the value at the root node. If the data to be inserted is greater than the value at the root node, you have to proceed right child of this root node. Step number 2, repeat step 1 until we meet an empty subtree where we can insert data in place of the empty subtree by creating a new node. So you have to repeat this step 1 until you met with an empty subtree, until you meet with an empty subtree where there is space for data insertion. And step number 3 is exit. Once you are done with this, once you found an empty space and you have compared all of the things, then you can insert the data and come out of this loop. Here are the algorithm steps we can see in proper fashion. New node is a pointer variable. See, here we will be making use of pointer variables. So new node is a pointer variable to hold the address of newly created node, and data is the information to be pushed in. Now step number 1, input the data to be pushed in and root node of the tree. Here you need to first give input as the value you need to insert into the tree. And also you need to know what is the root node value. Then you need to create a new node using new node equal to create new node. Okay. Now step number 3, here you need to check if root is null. If root is having no value, then your tree is empty tree. So we are checking if root is null. If so, then this root node becomes a new node. Step number 4 says that if step number 3 condition is false, then go for step number 4 and check if data to be inserted is less than the root node value. If so, then you have to make root is equals to root child and then go back to step number 4. You will be in this loop as long as the condition in the loop is true. Else you will come out of the loop and follow step number 5. If data is greater than root information, then make root is equals to root of the right child. And go to step number 4. Again you have to go to step number 4. If not, then check if data is less than the root information. If so, then make this root of left child equal to new node. Else if data is greater than root information, then make this root right child equal to new node. Else you can display duplicate node and exit from the loop. Step number 9 says new node information is equals to data. Also make some assignments like new node left child is equals to null and new node right child is also equal to null. And here your algorithm terminates. Now we'll try to understand this with the help of an example. Look here, we have at the root node we have here value as 45. The item we want to insert or the data we want to insert is 65. Okay. Now item is 65. We are checking that item, is it greater than the root node or is it less than the root node? We found that it is greater than the root node. So if so, what we need to do? We need to assign this root equal to root of right child. That means we are now at child having value 79. Then at step number 2, we will again check. Now this becomes the root. We'll check the item value across the root node value. We found that it is less than the root node. Okay. Since its left child is there, we'll proceed along the left child here. As you can see in step number 3. So now this node having value 55 becomes the root here. Now we will compare this item 65 with this root value 55. And we got to know that it is greater than this. So simply we'll make an insertion to the right child. That means now we will have a split from this node 55. We'll split an arm to the right side and insert value 65 here. I hope you all are following me. Okay, now the second operation that can be carried out on binary search tree is searching an element. That means you are looking for a particular data item in a binary search tree. So searching a node is easy because elements in binary search tree are sorted in a specific order. What order it maintains? Root is greater than left child and right child is greater than the root node. So this order is always followed. Step number 1 says compare the element to be searched with the root element of the tree. If the root is matched with the target element, then return the node's location. Else, check whether the item is less than the root node. If it is smaller than the root element, then move to the left subtree. If it is larger to the root node, then move to the right subtree. And repeat the above procedure recursively until the match is found. You have to go on repeating it until you find the element you are searching for. If the element is not found or not present in the tree, then return null. If you have finished with traversing till the end of the tree, till the leaf node of the tree, and still you did not find the element you are looking for, then simply return null here. Now here is an algorithm steps in a proper fashion. Input the data to be searched and assign the address of the root node to root. If data is equals to root information, then display data exists in the tree and go to step 6. If root is equals to null, then display data does not exist because here there are no more elements to be processed in the tree. And go to step number 6. If data is greater than root information, then make root is equals to right child of the root node and go to step 2. If data is less than the root information, then make root node is equals to root's left child and go to step 2. Now step number 6 says you have to stop here. Similarly, we can also operate deletion of an element in binary search tree. Now while deleting an element, you have to first search where the element is located. Then only you can delete it. Because when you delete a node, it again has to rearrange the tree in a proper fashion so that it maintains binary search tree property. So first search and locate the root node to be deleted. Then any one of the following condition arises. If the node to be deleted has no children, this is the first condition that arises. Second condition, the node has exactly one child, that is any one, either left or right subtree it has. The node has two